What if everything you thought you knew about the universe was just the surface of something far stranger? Right now, as you sit there watching this, the fabric of reality might be unfolding in ways you can't even see, dimensions hidden in plain sight, curled up so tightly they escape our senses. We're used to thinking in 3 dimensions: length, width, height, but what if space itself holds secrets our eyes were never built to perceive? This isn't science fiction. It's one of the most electrifying frontiers of modern physics, where the rules of reality bend, twist, and shatter our understanding of existence. Picture this: every time you move your hand, it might be passing through layers of reality you'll never feel, like a fish swimming through water without ever grasping the concept of air. Scientists call these hidden dimensions tiny, folded-up realms nested within the universe, so small they dwarf a single atom. Some theories suggest they could be the missing piece to gravity's weakness, or even gateways to parallel worlds. And here's the kicker: if these dimensions exist, they could rewrite everything we know about time, space, and the very nature of matter. That's what we're diving into today. 30 facts so mind-bending, they'll make you question the reality around you. From theories that stretch back to Einstein's wildest dreams to cutting-edge experiments hunting for echoes of these hidden layers, we're about to unravel the cosmos' best-kept secrets. So buckle up. By the end of this journey, the universe won't look the same, because once you peer beyond the veil of ordinary perception, there's no going back. Think about the space around you, the room you're in, the screen in front of you, even your own hands. Everything seems to exist in 3 simple dimensions: length, width, and height. But what if that's just the tip of the cosmic iceberg? For decades, physicists have been wrestling with an idea so radical. It turns our everyday reality upside down: the possibility that our universe isn't just 3-dimensional, but 10 or even 11. That's the mind-bending promise of string theory, one of the most ambitious frameworks in modern physics. Here's how it works at the tiniest scales, far smaller than any microscope could ever see. The fabric of space might not be smooth and flat like a tabletop. Instead, it could be curled up into intricate, hidden shapes, extra dimensions folded so tightly they're practically invisible. Imagine a garden hose lying on the ground. From a distance, it looks like a simple line, one-dimensional, but get close enough and you realize it's actually a tube with a circular dimension wrapped around it. Now shrink that idea down to the size of a single atom, and you've got the essence of how these extra dimensions could be hiding in plain sight. Why would the universe bother with such complexity? Because without these hidden layers, some of the deepest mysteries of physics, like why gravity is so weak compared to other forces, might never make sense. Picture gravity as a force that doesn't just pull through our familiar 3 dimensions, but leaks into these unseen folds, diluting its strength. It's like trying to hear a whisper in a vast, echoing cathedral. Some of the sound gets lost in the unseen architecture. And here's where it gets wild. If these extra dimensions exist, they're not random. They're mathematically precise, their shapes determining the very laws of nature. The way they vibrate could dictate why particles have mass, why light behaves the way it does, even why time flows in one direction. It's as if the universe has been playing an intricate symphony all along. We just never had the instruments to hear the full composition. Now you might wonder, if these dimensions are real, why can't we detect them? The answer lies in their size. Current theories suggest they could be curled up at scales 1 billion times smaller than an atom's nucleus, far beyond anything our most advanced colliders can probe. But that hasn't stopped scientists from hunting for clues. Some experiments look for microscopic black holes that might wink into existence if extra dimensions are leaking gravity. Others search for anomalies in particle collisions that could hint at hidden layers of reality. So next time you reach for your coffee or scroll on your phone, remember, you might be moving through a reality far richer than meets the eye. The universe, it seems, has more than a few tricks up its sleeve. Long before string theory dazzled physicists with its 11 dimensions, a pair of visionary scientists were already playing with fire by adding an extra dimension to Einstein's universe. In 1921, mathematician Theodore Kaluza made a jaw-dropping discovery. By rewriting Einstein's equations in 5 dimensions instead of 4, something miraculous happened. Suddenly, the equations didn't just describe gravity, they also perfectly captured Maxwell's laws of electromagnetism. It was as if the universe had been hiding a secret connection between these two forces all along, waiting for someone bold enough to peek behind the curtain of space-time. Kaluza's idea was so radical that even Einstein hesitated for 2 years before publishing it. Picture this, just one new dimension, curled up so small it's invisible, could unite gravity's cosmic dance with the crackle of electric fields. Swedish physicist Oskar Klein later refined the theory in 1926, suggesting this 5th dimension might be compactified, a term physicists use for dimensions rolled up tighter than a coiled spring. To understand how this works, think of an ant walking along a telephone wire. From far away, the wire looks one-dimensional. The ant just moves forward or backward. But up close, there's a second dimension. The ant could circle the wire's circumference too. Now imagine that circular path is 1 billion times smaller than an atom. That's Klein's vision of the 5th dimension, a hidden loop woven into every point in space. What makes Kaluza-Klein theory revolutionary isn't just the math, it's the philosophical shift. For the first time, physicists realized that dimensions might not just be empty stages where physics plays out, they could actively shape the forces governing our universe. Electromagnetism, in this view, isn't a separate phenomenon, it's gravity's shadow, cast from higher dimensional geometry we can't perceive directly. It's like discovering that the echoes in a cathedral aren't random noise, but actually contain hidden messages about the building's hidden architecture. But here's where things get thorny. When quantum mechanics came roaring onto the scene, Kaluza-Klein theory hit a wall. The math worked beautifully for gravity and electromagnetism, but it couldn't explain the newly discovered strong and weak nuclear forces. Plus, there was no experimental proof, no way to peek into that tiny, coiled 5th dimension. For decades, the idea gathered dust until string theorists dusted it off and realized Kaluza and Klein might have been onto something far bigger than they imagined. Today, their work is seen as the first crack in the dam of 3-dimensional thinking. Modern theories like string theory and M-theory didn't abandon Kaluza-Klein's approach, they supercharged it, suggesting that 6 or 7 extra dimensions could be curled up in Calabi-Yau shapes, each vibrating to produce different particles and forces. It's as if Kaluza and Klein planted an acorn, and centuries later, physicists found themselves standing in the shadow of a redwood. So next time you flip a light switch or feel gravity's pull, remember, those forces might be whispering secrets from dimensions just beyond our grasp. The universe, it seems, has always been richer than we dared to dream. Now imagine our entire universe as just one thin slice in a cosmic loaf of bread, a single 3-dimensional membrane drifting in a space far vaster and stranger than we can perceive. This is the mind-bending idea at the heart of brane world theory, a radical twist on M-theory that suggests our reality might be stuck to the surface of something much bigger. Think of it like a piece of paper floating in a room while we can move freely across its flat surface. We'd never notice the immense space above or below us unless something from that higher dimension reached in. In this framework, our universe isn't just embedded in higher dimensions, it's trapped there, like a soap bubble clinging to the surface of a pond. Physicists call these bubbles branes, short for membranes, and they could come in all shapes and sizes. Some might be 3-dimensional like ours, while others could have completely different physics, vibrating with forces and particles we can't even imagine. The higher dimensional space they float in, that's called the bulk, and it's the ultimate backstage of reality where universes might collide, gravity could leak between branes, and even time itself might behave differently. Here's where it gets even wilder. What if gravity's puzzling weakness isn't a flaw in our theories, but a clue? In some brain world models, gravity isn't confined to our membrane like the other forces. It's free to spread out into the bulk, diluting its strength like sunlight fading as it travels through space. That could explain why gravity feels so feeble compared to electromagnetism or the nuclear forces. It's not weak, just spread thin across dimensions we can't see. Picture a magnet clinging to your fridge. The electromagnetic force holds it tight against gravity's pull, not because gravity is inherently weaker, but because most of its influence is leaking into hidden layers of reality. And if brains exist, they might not be alone. Parallel universes could be floating just millimeters away in the bulk, separated from us by an invisible gulf of higher dimensions. In some scenarios, these nearby brains might even bump into each other, triggering cosmic-scale events like the Big Bang itself. It's like two sheets of paper drifting in a breeze. When they touch, the collision could unleash enough energy to birth an entire new universe. Some scientists speculate that our own universe might bear the scars of such an encounter in the faint ripples of the cosmic microwave background. Yet for all its elegance, the brain world idea raises dizzying questions. If other universes are floating out there, could anything cross the gap? Could there be civilizations in the bulk navigating dimensions we're utterly blind to? And if gravity really leaks into higher dimensions, why haven't we detected its absence? Experiments like the Large Hadron Collider have hunted for signs of extra dimensions like microscopic black holes that would evaporate instantly. But so far, the bulk remains frustratingly silent. But silence isn't proof. The universe has surprised us before, and if brain world theory is right, we're living on the surface of a reality far grander and far stranger than we ever dreamed. Every galaxy, every star, every atom might just be the three-dimensional tip of an 11-dimensional iceberg. So the next time you look up at the night sky, ask yourself, are we alone on our membrane, or is the bulk teeming with worlds we'll never see? What if the three-dimensional world we experience every day is nothing more than an elaborate illusion, a hologram projected from information encoded on a distant, two-dimensional surface? This isn't the plot of a sci-fi movie, it's the startling premise of the holographic principle, one of the most provocative ideas in theoretical physics. The concept suggests that everything we perceive, the depth of a canyon, the curve of a planet, even the sensation of moving through space, might just be a cosmic trick, a shadow cast by data etched onto the universe's outermost boundary. The roots of this idea trace back to an unexpected place, black holes. In the 1970s, physicist Jacob Bekenstein made a groundbreaking discovery: black holes have entropy, a measure of disorder often linked to information. But here's the twist: that entropy doesn't scale with the black hole's volume, as you'd expect for a three-dimensional object. Instead, it's proportional to the surface area of its event horizon, the point of no return. It's as if all the information about what falls into a black hole isn't lost inside its depths, but smeared like invisible ink across its two-dimensional surface. This revelation led physicists like Leonard Susskind and Gerard T. Hooft to a radical hypothesis. If a black hole's interior can be perfectly described by information on its boundary, could the same be true for our entire universe? Imagine a cosmic version of a hologram where the three-dimensional image on your credit card isn't stored inside the plastic, but encoded in microscopic patterns on its flat surface. The holographic principle takes this analogy to the extreme, proposing that every star, planet, and particle in our universe might just be a projection from a vast two-dimensional canvas at the edge of reality. But how could something as tangible as a mountain or as vivid as a sunset be reduced to data on a flat screen? Think of it like a video game. The immersive worlds you explore on screen aren't actually inside your monitor. They're generated by code, mathematical rules that create the illusion of depth. In the holographic universe, the laws of physics might work the same way, with our 3D reality emerging from quantum bits flickering on a distant two-dimensional surface. Even time and space themselves could be secondary, like the glow from a light bulb, real to our senses but not fundamental. The implications are staggering. If dimensions are illusions, then the very fabric of reality might be simpler and stranger than we ever imagined. Gravity, quantum mechanics, even the arrow of time could all be side effects of information processing on that grand cosmic boundary. It's a theory so audacious that even its proponents admit it feels like science fiction. But here's the kicker. If the holographic principle is correct, we're not just living in the universe, we're living in its shadow, a shimmering projection of something far more profound. Deep in the heart of string theory lies a mathematical puzzle so intricate, it might hold the key to our universe's hidden architecture, the enigmatic Calabi-Yau shapes. These six-dimensional geometries are where the extra dimensions of string theory curl up, vanishing from our perception like whispers lost in a storm. To grasp how they work, picture a single point in space, a dot so small it has no size at all. Now imagine that dot isn't empty. Instead, it's a tightly folded universe unto itself, with 6 extra dimensions coiled into patterns so complex they resemble origami crafted by the cosmos. The beauty of Calabi-Yau shapes isn't just in their complexity, it's in what they explain. In string theory, the vibrations of tiny, one-dimensional strings determine the properties of every particle in existence. But for the math to work, these strings can't just dance through our familiar 3 dimensions. They need room to move 9 spatial dimensions plus time. That's where Calabi-Yau manifolds come in. Like the hidden grooves of a lock waiting for the right key, these shapes provide the exact geometry needed to compactify those extra dimensions, tucking them away so neatly that all we experience are the echoes of their influence. Think of it like crumpling a piece of paper into a tight ball. From across the room, it looks like a simple speck, a zero-dimensional point, but up close you'd see valleys, ridges, and folds giving it structure. Calabi-Yau shapes are the universe's version of that paper ball, but with dimensions we can't touch or see. Their folds create the stage upon which strings vibrate, and the way those vibrations resonate through the geometry determines everything from the mass of an electron to the strength of gravity itself. Here's where it gets even wilder. The exact shape of these hidden dimensions could be the reason our universe looks the way it does. Change even one tiny loop or twist in a Calabi-Yau manifold, and the laws of physics might unravel entirely. Electromagnetism could vanish, quarks might not bind into protons, even time could flow differently. It's as if these shapes are cosmic tuning forks, their vibrations setting the pitch for reality itself. Yet for all their elegance, Calabi-Yau shapes remain frustratingly out of reach. We can't peer into dimensions smaller than atoms, and no experiment has yet detected their presence. But mathematicians and physicists keep searching, because if these geometries are real, they're not just hidden features of the universe, they're its blueprint. Every galaxy, every photon, every breath you take might just be the shadow of strings dancing through dimensions we'll never see. So the next time you feel the solidity of the ground beneath your feet, remember, reality might be far more delicate and far more dazzling than it seems. Gravity might seem powerful when you watch an apple fall or feel the weight of a backpack, but in the grand scheme of the universe's forces, it's shockingly feeble. Compared to electromagnetism, the force that holds atoms together and powers every light bulb, gravity, is a whisper in a hurricane. A fridge magnet, using nothing but electromagnetic forces, can defy the entire gravitational pull of Earth. This cosmic imbalance has puzzled scientists for decades. Why is nature so lopsided? One tantalizing answer might lie in dimensions we can't see. Imagine gravity isn't just tugging along the 3 dimensions we know, length, width, and height, but seeping into hidden, folded-up layers of reality. Picture a sponge soaked with water. Most of the liquid isn't on the surface but trapped inside its tiny crevices. Similarly, gravity's influence might be diluted because much of it escapes into extra dimensions, leaving only a faint trace in our familiar world. This idea isn't just wild speculation. Some versions of string theory and brane world models suggest that while particles like electrons and quarks are pinned to our three-dimensional membrane, gravity could be free to wander the higher dimensional bulk, spreading its strength thin across realms we'll never perceive. Scientists have devised ingenious ways to test this theory. If gravity leaks into extra dimensions, its influence should weaken dramatically at incredibly small distances, scales far tinier than the width of an atom. Experiments using devices like torsion balances or microscopic cantilevers measure the gravitational pull between objects separated by mere microns, searching for any deviation from Newton's laws. Other researchers monitor neutron stars and black holes for anomalies that might betray gravity's hidden pathways. Even the Large Hadron Collider has joined the hunt, attempting to produce microscopic black holes that would evaporate in an instant if extra dimensions exist. The stakes couldn't be higher. If gravity's weakness is really a clue to hidden dimensions, it would rewrite our understanding of reality's fabric. But so far, the universe isn't giving up its secrets easily. Every experiment returns the same frustrating result. No deviation, no leak, no trace of those elusive extra dimensions. Yet absence of evidence isn't evidence of absence. The universe has surprised us before, and if hidden dimensions are real, we might be standing at the brink of a revolution as profound as Einstein's relativity. After all, gravity didn't get weaker. We might just be seeing less of it than actually exists. Most of us assume the hidden dimensions of string theory must be impossibly tiny, curled up smaller than an atom. But what if some are hiding in plain sight, stretching as large as a millimeter across? This startling idea comes from the large extra dimensions model, where gravity's puzzling weakness isn't due to minuscule folds in space-time, but because it's leaking into dimensions big enough to see with the naked eye, if only we knew where to look. The math behind this is both simple and profound. In our everyday world, gravity's strength follows Newton's inverse square law: double the distance between two objects, and the gravitational pull drops by a factor of 4. But if gravity can spread into extra dimensions, that power law changes. Picture a garden hose spraying water in 3 dimensions. The water pressure drops with distance, as you'd expect. Now poke holes along the hose's length. Suddenly, water leaks into unseen directions, weakening the spray far faster than before. That's essentially what could be happening with gravity, except the holes lead to dimensions we can't perceive. Here's the twist: we wouldn't notice these millimeter-sized dimensions in daily life because the particles that make up matter, electrons, quarks, even light itself, might be trapped on our 3-dimensional membrane, unable to venture into the higher dimensional bulk. Only gravity, the odd one out among forces, could slip through. It's like living in a house where the walls are porous to sound but solid to everything else. You'd hear echoes from unseen spaces without ever finding their source. Experiments are already hunting for these elusive dimensions. Scientists use devices so sensitive they can measure gravitational forces between objects placed just a hair's width apart. If gravity suddenly weakens at sub-millimeter scales, it could betray the presence of extra dimensions lurking right under our noses. Another clue might come from particle colliders. If energy escapes into large extra dimensions during collisions, it would look like missing momentum in detector readings. Yet the universe guards its secrets well. So far, no experiment has found definitive proof of these hidden realms. But absence of evidence isn't proof of absence after all. Who would have guessed a century ago that invisible particles like neutrinos flood the cosmos? The search continues because if large extra dimensions exist, they wouldn't just rewrite physics textbooks, they'd prove we've been sharing our universe with invisible giants all along. What if the person standing next to you isn't just another human, but an entirely different version of reality, separated from our universe by less than the width of a fingernail? This isn't just speculation, it's a direct consequence of brane world theory, where our cosmos might be one of countless membranes floating in a higher dimensional void. Picture two sheets of paper suspended parallel in midair, so close they nearly touch, yet utterly unaware of each other's existence. Now replace those sheets with entire universes, each with its own stars, planets, and perhaps even life, drifting silently in dimensions we can't perceive. The math behind this is staggering. In some models, these parallel branes could be mere millimeters apart in the bulk. The higher dimensional space they inhabit, yet completely unreachable because the distance between them isn't measured in our familiar 3 dimensions. It's like two people standing back to back in a pitch-black room, each convinced they're alone, unaware that their shadows are centimeters apart in a direction neither can see or move through. The forces that bind particles to our brane electromagnetism, the nuclear forces, act like cosmic glue, preventing anything from crossing the gap. Only gravity, the odd force out, might subtly betray the presence of neighboring worlds by weakly tugging between brane. Here's where it gets even stranger. Collisions between these membranes could be the ultimate cosmic reset buttons. When branes drift too close in the bulk, their collision might unleash energy so vast it triggers a new Big Bang, essentially birthing a fresh universe. Some theorists argue our own cosmos might carry scars of such an encounter in the faint temperature variations of the cosmic microwave background, the afterglow of creation. It's a cyclical vision of reality where universes don't just exist alongside one another. They periodically collide, die, and rebirth in an endless higher dimensional dance. But what would these parallel realities look like? The possibilities stretch the imagination. A nearby brane might host a universe nearly identical to ours, where every choice you didn't make played out differently. A world where dinosaurs never went extinct or where electricity remained undiscovered. Others could be utterly alien, with physics so bizarre that matter can't form stable atoms, or where time flows backward, the most haunting possibility. Some branes might be so close that their gravitational whispers subtly influence ours, creating unexplained anomalies like dark matter, which some theories suggest could be the gravitational pull of a neighboring universe bleeding into ours. Yet for all its grandeur, the multiverse hypothesis faces fierce skepticism. Without experimental proof, it risks becoming untestable philosophy rather than hard science. But researchers aren't giving up. Some hunt for gravitational anomalies, tiny ripples that might betray a nearby brane's presence. Others simulate brane collisions in supercomputers, searching for patterns that match our universe's infancy. The irony is delicious. The very dimensions hiding these parallel worlds might also be the key to finding them. After all, if the universe has taught us anything, it's that reality's deepest truths often lie just beyond the edge of perception. So next time you glance at the empty space around you, consider this. The void might be far from empty. It could be teeming with unseen worlds, separated from us by less than the gap between your fingers, realms where every possible version of existence plays out in dimensions we'll never walk, but whose echoes might shape the cosmos we call home. Quantum entanglement is already bizarre enough. Particles linked across vast distances, instantly mirroring each other's states no matter how far apart they are. Einstein famously called it spooky action at a distance, because it defies our everyday intuition about how information should travel. But what if this spookiness isn't just a quirk of quantum mechanics? What if it's a clue that entangled particles are exploiting hidden dimensions, slipping outside spacetime's rules to communicate through unseen backdoors? Picture entanglement like two ends of a wormhole, except instead of a tunnel through space, the connection might thread through higher dimensional folds we can't perceive. Imagine two ants on opposite sides of a crumpled piece of paper. To us, they seem far apart, but if the paper folds just right, their positions could touch in an unseen dimension. Similarly, entangled particles might appear separated in our three-dimensional world while actually being neighbors in a hidden direction, their links stretching through dimensions where distance and time work differently. This idea isn't pure speculation. Some quantum gravity models suggest that entanglement and spacetime might emerge from the same deeper structure, like two sides of a coin. In this view, when particles become entangled, they're not sending signals faster than light. They're revealing a pre-existing connection woven into the fabric of reality itself, where hidden dimensions provide shortcuts our classical physics can't map. It's as if spacetime is just the surface of a much deeper ocean, and entanglement is the ripples betraying currents beneath. Could we ever test this? Experiments with quantum systems might hold the key. If extra dimensions influence entanglement, subtle anomalies could appear in how particles correlate over extreme distances, deviations from what standard quantum mechanics predicts. Some physicists even propose that black holes, those cosmic shredders of information, might preserve data in higher dimensions through entangled particles, offering a backdoor escape from the infamous information paradox. The implications are staggering. If entanglement relies on hidden dimensions, then quantum weirdness isn't a bug in reality, it's a feature, pointing toward a universe far more interconnected than we ever imagined. Every time particles sync across light years instantaneously, they might be whispering the same truth. The dimensions we see are just the beginning. Dark matter is the universe's most frustrating ghost, an invisible substance that makes up 85% of all matter, yet refuses to interact with light or any of our telescopes. We only know it's there because its gravitational grip holds galaxies together, keeping stars from flying apart like sparks from a bonfire. But what if dark matter isn't just hiding in plain sight? What if it's operating in dimensions we can't access? Its particles drifting through folds of reality our instruments were never built to detect. This idea starts with a simple observation. Gravity is the only force dark matter seems to obey. Unlike normal matter, it doesn't collide, reflect light, or emit energy. It's as if dark matter exists on a parallel stage, shadowing our universe without ever stepping into the spotlight. Some theories suggest that's exactly what's happening. Dark matter particles could be moving through extra dimensions, their gravitational influence leaking into our world like footsteps echoing through a wall. Picture a ship sailing on the ocean. You see its wake distorting the water's surface, but the vessel itself remains submerged, invisible beneath the waves. Dark matter might work the same way. Its effects ripple through our three-dimensional cosmos, while its true form remains anchored in higher dimensional depths. The math behind this is surprisingly elegant. If dark matter interacts primarily in extra dimensions, its particles wouldn't need to obey the strict rules of our familiar physics. They could be massive yet intangible, like shadows cast by objects in a room we can't enter. This could explain why efforts to detect dark matter directly in underground labs with ultra-sensitive detectors keep coming up empty. We're not just looking for a needle in a haystack, we're trying to find a needle that only exists in a direction we can't point to. But here's where the theory gets truly compelling. If dark matter is a dimensional traveler, it might leave subtle fingerprints in the way galaxies rotate or how galaxy clusters collide. Astronomers have noticed that dark matter's distribution in space isn't perfectly smooth. It clumps in ways that don't always match predictions. Could these anomalies be hints of higher dimensional geometry warping its behavior? Some researchers even speculate that dark matter's strange halos around galaxies aren't just blobs of invisible stuff, but gravitational shadows cast by structures vibrating in unseen dimensions. Of course, the challenge is proving any of this. Without a way to probe those hidden dimensions directly, dark matter remains a puzzle with pieces missing. But that hasn't stopped scientists from devising clever workarounds. Some experiments search for exotic particles that might occasionally bump into our dimension, leaving fleeting signals in particle colliders. Others study the cosmic microwave background for patterns that could reveal dark matter's multidimensional origins. The irony is delicious. The very thing that makes dark matter so elusive, its refusal to play by our rules, might be the clue that cracks the case. If this theory holds, the universe's missing mass isn't lost at all. It's just operating on a stage we've yet to see. Its presence a constant reminder that reality has layers we're only beginning to uncover. So the next time you gaze at the night sky, remember the darkness between the stars might not be empty. It could be teeming with entire dimensions of matter, their secrets written in gravity's silent script. At the frontiers of physics, where theories bend and reality's fabric stretches thin, scientists have built the ultimate detective tool for hidden dimensions, the Large Hadron Collider. This 17-mile ring beneath the French-Swiss border doesn't just smash particles at near-light speeds, it's hunting for echoes of higher dimensional realms. Picture this: when protons collide with enough energy, they might not just shatter into familiar particles. They could momentarily punch through the membrane of our three-dimensional world, creating microscopic black holes or sending gravitational waves called gravitons fleeing into dimensions we can't see. These black holes wouldn't be the cosmic monsters that swallow stars. Instead, they'd be vanishingly small, existing for just a fraction of a second before evaporating in a burst of radiation, a signature physicists call Hawking radiation. It's like throwing a pebble into a pond and watching the ripples, except the pond is space-time itself, and the ripples might reveal where the water spills into hidden channels. The math suggests that if extra dimensions exist at the scales predicted by some string theory models, the LHC's collisions should produce these tiny black holes at a rate we could detect. Gravitons, the hypothetical particles carrying gravity's force, offer another tantalizing clue. Unlike photons or electrons, gravitons might not be confined to our three-dimensional brain. They could slip into the bulk, the higher dimensional space surrounding us. If that's true, particle collisions might sometimes appear to lose energy, as if something invisible carried it away. The LHC's detectors are fine-tuned to catch these discrepancies, searching for events where momentum seems to vanish into thin air, or more accurately, into dimensions we can't perceive. The challenge is separating these extraordinary signals from ordinary quantum noise. It's like listening for a whisper in a thunderstorm. Every collision produces a cacophony of particles, and spotting the faint signature of extra dimensions requires sifting through mountains of data. That's where machine learning steps in, algorithms trained to recognize the subtlest anomalies, the telltale fingerprints of physics beyond our current understanding. So far, the LHC hasn't found definitive proof of microscopic black holes or graviton escape routes, but absence of evidence isn't the end of the story. The collider might simply need more energy, higher velocities to pierce through spacetime's veil. Future upgrades could push its limits further, probing scales where hidden dimensions might finally unveil themselves. Until then, every collision is a roll of the cosmic dice, a chance that this time reality will crack open just wide enough to show us what's lurking beyond. The stakes couldn't be higher. If the LHC ever catches a graviton slipping into the bulk or detects a black hole evaporating into extra dimensions, it wouldn't just confirm string theory, it would rewrite our place in the cosmos. We'd no longer be three-dimensional beings in a three-dimensional world, but shadows cast on the surface of something infinitely deeper. And that's the beauty of the hunt. Every time particles clash in that underground ring, they're not just testing theories. They're probing the very architecture of existence, asking the universe if it's ready to reveal its best-kept secrets. Imagine two metal plates placed so close together in a vacuum that the space between them is narrower than a strand of DNA. According to classical physics, nothing should happen, but in the bizarre realm of quantum mechanics, these plates experience an invisible force pushing them together. This is the Casimir effect, a phenomenon so subtle it was only confirmed in the late 20th century. yet it might hold tantalizing clues that extra dimensions are tugging at reality from just beyond our perception. Here's how it works. Even in empty space, quantum fields constantly flicker with virtual particles, pairs of matter and antimatter that pop in and out of existence too fast to detect directly. But when two plates are brought extremely close, they restrict the wavelengths of these virtual particles that can exist between them. Outside the plates, quantum fluctuations continue unhindered, creating a pressure differential that pushes the plates together. Think of it like being in a crowded elevator where everyone shifts slightly. Those tiny movements add up to an unmistakable force. Now, here's where hidden dimensions enter the picture. If extra dimensions are curled up at microscopic scales, they could alter the behavior of these quantum fluctuations in ways standard models don't predict. The Casimir effect is exquisitely sensitive to the geometry of spacetime. Even distortions smaller than an atom's nucleus could tweak the force between the plates. Some theories suggest that if compactified dimensions exist, their presence might subtly amplify or shift the Casimir force at specific distances, like a hidden hand bending the rules of quantum foam. Experimentalists are already chasing this possibility. Precision instruments like atomic force microscopes can now measure Casimir forces at nanometer separations, searching for deviations that might betray the influence of higher dimensions. Other researchers simulate how different compactified geometries, from Calabi-Yau shapes to Klein bottles, would warp the expected quantum pressure. It's like listening for faint echoes in a cave. If the reverberations don't match predictions, it might mean the cavern has chambers we can't see. The implications are staggering. If the Casimir effect ever shows anomalies tied to hidden dimensions, it wouldn't just confirm string theory, it would revolutionize our understanding of emptiness itself. The vacuum of space might not be empty at all, but a seething, multidimensional landscape where every cubic centimeter hums with energies from unseen directions. So the next time you see two objects clinging together against expectation, remember, they might not just be obeying quantum laws, but whispering secrets about dimensions folded smaller than imagination can reach. Neutrinos are the universe's most elusive escape artists, ghostly particles that pass through entire planets like they're not even there. Billions stream through your body every second, leaving no trace. Yet these cosmic phantoms have a quirk that defies explanation. They change identities as they travel, oscillating between three known types: electron, muon, and tau neutrinos. But here's the twist. Some experiments detect more oscillations than the standard model of physics can account for. Could this anomaly be the first whisper of neutrinos brushing against hidden dimensions? Think of neutrinos as chameleons moving through a forest. Normally, they shift between three colors: red, blue, and green, as expected. But occasionally, they flicker into a shade we've never seen before, vanishing from detection before reverting to a known state. This missing neutrino behavior has led some physicists to propose a radical idea. What if these particles aren't just oscillating between three flavors, but momentarily slipping into extra dimensions where they adopt properties our instruments can't measure? The math behind this is as elegant as it is mind-bending. If compactified dimensions exist, neutrinos, unlike other particles, might have just the right mass and interactivity to field them. Picture a guitar string vibrating not just along its length, but in tiny, coiled-up directions too small to see. Similarly, a neutrino's quantum wave could ripple into hidden dimensions, altering its oscillation pattern in ways that leave gaps in our observations. Experiments like Mini BUNI at Fermilab have spotted excess neutrino events that defy expectations, while IceCube in Antarctica has detected high-energy neutrinos with unexplained energy losses. These anomalies could be statistical noise, or they might be fingerprints of higher dimensional physics. Some models even suggest that sterile neutrinos, hypothetical particles that don't interact with any known force, could be neutrinos' higher dimensional counterparts, occasionally bleeding into our universe like echoes from a parallel room. Of course, skepticism runs deep. Alternative explanations like flaws in detector calibration or unknown nuclear effects could account for the data. But if neutrinos truly are dimension hoppers, the implications would rewrite particle physics. Suddenly, their bafflingly small masses and reluctance to interact make eerie sense. They're not just passing through our world, but skimming its edges, dancing along the borders of reality we can't yet map. The hunt for answers is on. Next-generation detectors like Dune will track neutrinos with unprecedented precision, searching for oscillation patterns that betray hidden dimensions' influence. Until then, every anomalous neutrino event is a cosmic riddle asking us, are we seeing glitches in our models or glimpses of a far richer universe lurking just beyond the veil? Time flows like a river, or at least that's how it feels to us. We move forward through it, unable to pause, rewind, or jump ahead. But what if this linear march of moments isn't the whole story? Einstein shattered the idea of absolute time over a century ago, proving it's interwoven with space into a single fabric spacetime, the universe's four-dimensional stage. Yet if higher dimensions exist, time might not just be a dimension. It could be a playground with loops, folds, and shortcuts that make our one-way experience seem quaint. Think of spacetime as a roll of film. Each frame is a snapshot of the universe at one instant, and the reel's length represents time. Normally, the projector only runs forward. But add extra dimensions, and suddenly, the film might twist into shapes where the frames touch in unexpected ways, like a Möbius strip where past and future blend into one continuous surface. In such a universe, time travel wouldn't require a DeLorean. It might just mean finding the right higher dimensional path, a cosmic backdoor linking distant moments. The math behind this is more than speculative fiction. Solutions to Einstein's equations, like Gödel's rotating universe or traversable wormholes, hint that closed time-like curves paths that loop back to their own past could exist if spacetime warps in just the right way. And if hidden dimensions are real, they might provide the geometry needed to stabilize these time warps without collapsing into paradoxes. Picture a hamster running on a wheel. From the hamster's perspective, it's moving forward endlessly, but from outside, its path is a circle. Higher dimensions could turn time into that wheel, with our linear perception just the view from inside the loop. But here's where it gets thorny. If time isn't strictly linear, why don't we meet tourists from the future? Some theories suggest nonlinear time might only be accessible at quantum scales or in extreme gravitational fields, like near a black hole's singularity, where spacetime stretches thin enough for higher dimensional effects to peek through. Others propose that branching timelines in extra dimensions prevent paradoxes, so every possible past and future plays out somewhere, just not where we can see. It's like holding a deck of cards. Each card is a version of reality, and time shuffles them in directions we can't follow. The most tantalizing clue might come from quantum mechanics itself. Particles like electrons don't behave as if they're bound by a single timeline. They exist in superpositions, seemingly touching multiple moments at once until measured. Could this quantum weirdness be a hint that time's flow is an illusion, a shadow cast by interactions we don't yet understand? If so, hidden dimensions might be the key to unlocking time's true nature, not as a river, but as an ocean with currents and eddies we've only begun to navigate. So the next time you check your watch or feel the weight of a deadline, remember, the ticking clock might just be the universe's way of keeping things simple for us three-dimensional beings. Beyond our perception, time could be bending, twisting, and folding in ways that make now far more mysterious than we ever imagined. Take a close look at a jagged coastline from above, say, Norway's rugged edges or the intricate bays of Maine. At first glance, it seems like a simple curve, something you could measure with a ruler. But zoom in, and the details multiply. Smaller inlets within larger ones, rocky protrusions repeating the same uneven patterns down to the tiniest scales. This isn't just irregularity, it's a glimpse into nature's hidden mathematical playbook, where dimensions aren't just whole numbers like 1, 2, or 3, but fractions in between. Welcome to the mind-bending world of fractals, where reality defies the clean lines of classical geometry and spills into dimensions we never knew existed. Fractals are shapes that repeat their complexity at every scale, like a cosmic hall of mirrors. A snowflake's branching arms, the veins of a leaf, even the branching networks of your lungs, all share this recursive quality where tiny parts echo the whole. But here's the twist: these patterns don't fit neatly into our usual dimensions. Mathematicians describe them with fractional dimensions, numbers like 1.26 or 2.72, quantifying how densely they fill space. Picture a ball of crumpled paper. From afar, it looks like a three-dimensional sphere, but up close, its creases and folds give it a dimension somewhere between 2 and 3. The coastline works the same way. It's too crinkled to be a one-dimensional line, yet not solid enough to be a two-dimensional plane. It exists in the fractal in between. The implications are staggering. If nature routinely builds with fractional dimensions, could space-time itself have fractal properties at quantum scales? Some theories suggest that at the tiniest levels, the fabric of reality might resemble a fractal infinitely detailed, with dimensions that fluctuate like the coastline's jagged edge. This could explain quirks in quantum mechanics, where particles behave as if they're navigating a space more complex than our smooth, classroom geometry version of the universe. Imagine walking through a forest where every step takes you deeper into a maze that's somehow the same at every scale. That's the eerie symmetry of a fractal cosmos. Even gravity might play by fractal rules. Some models propose that dark matter's elusive distribution resembles fractal patterns, clustering in ways that defy traditional geometry. Galaxies aren't scattered randomly. They form vast, web-like structures with voids and filaments repeating across cosmic distances, a hint that the universe's large-scale architecture mirrors the branching complexity of a fern or lightning bolt. But the real magic lies in how fractals blur the boundaries between dimensions. A broccoli floret, for instance, packs so much surface area into a small volume that it behaves almost like a three-dimensional object with a two-dimensional blueprint. Evolution favors these designs because they're efficient. Lungs maximize oxygen absorption, roots optimize water intake, all by exploiting dimensions beyond the obvious. It's as if life hacked the geometry of the universe, using fractal math to fold infinity into finite spaces. So the next time you see a river delta as twisting branches or the frost etching your window, remember, you're not just looking at beauty. You're witnessing dimensions unspooling in real time, a silent testament to the fact that reality doesn't play by integer rules. The universe, it seems, prefers its dimensions messy, wild, and gloriously in between. What if our universe wasn't born from a single explosive moment, but from the slow, cosmic collision of two hidden worlds? This is the heart of the ekpyrotic universe theory, a radical twist on the Big Bang that replaces the fiery singularity with something far stranger. Two vast, floating membranes in higher dimensional space, drifting toward each other until their impact sets the stage for everything we know. Imagine two sheets of paper suspended in a dark room, silently drawing closer over eons. When they finally meet, the energy of their collision doesn't tear them apart. It ignites a new universe along their shared surface, like sparks flying from a blacksmith's anvil. This idea didn't come from nowhere. It builds on the same brain world concepts we've seen before, but with a crucial twist. Instead of brains drifting apart, they're destined to crash together over and over in an endless cycle. The name ekpyrotic comes from the ancient Greek word for conflagration, a fitting nod to the theory's vision of creation through collision. But unlike the classic Big Bang's hot, dense starting point, the ekpyrotic model suggests our universe began cold and nearly silent, its structure imprinted by the geometry of that primordial clash. Here's how it works. Picture our three-dimensional universe as a membrane, one of many floating in a higher dimensional bulk. Nearby, another brane drifts parallel to ours, separated by a gap so small it's invisible to us, yet vast enough to shape cosmic history. Gravity tugs these branes together over unimaginable timescales, and when they collide, their kinetic energy transforms into the matter, radiation, and dark energy that fill our cosmos. It's like clapping your hands. The sound waves that ripple out aren't part of your palms. They're the energy of the impact made audible. In the ekpyrotic scenario, the Big Bang is that sound, echoing through our brain as the universe we inhabit. What makes this model so compelling isn't just its elegance. It solves puzzles that plague standard cosmology. The Big Bang leaves us with head-scratchers like the horizon problem, why far-flung regions of space look so similar despite never being in contact, and the universe's startlingly flat geometry. Inflation theory patches these holes by proposing a brief period of hyper-expansion right after the bang. But the ekpyrotic universe offers an alternative. The slow, steady approach of the branes before collision naturally stretches and flattens space, ironing out wrinkles without needing a separate inflation mechanism. It's as if the universe pressed its own shirt before putting it on. But the real mind-bender is the cyclical nature of the theory. After the collision, the branes rebound like springs, drifting apart before gravity pulls them back for another encounter. Each crash could birth a new universe, meaning our cosmos might be just one link in an endless chain of creations, each with slightly different physics based on the angle and energy of the impact. Some versions of the theory even suggest that dark energy, the mysterious force accelerating the universe's expansion, is a shadow of the next approaching brane, its gravitational tug subtly warping space-time as the cycle prepares to repeat. Of course, skeptics raise valid questions. If branes keep colliding, why don't we see evidence of previous cycles? The answer might lie in the sheer violence of each rebirth. The heat and chaos of a new Big Bang could erase all traces of earlier universes, like waves smoothing footprints from a beach. Others wonder how the branes avoid sticking together after collision, or how quantum fluctuations during the crash generate the precise patterns we see in the cosmic microwave background. These aren't trivial challenges, but proponents argue they're no more daunting than the mysteries inflation leaves unresolved. The most tantalizing hint might come from the fabric of spacetime itself. If the ekpyrotic model is correct, the universe's primordial gravitational waves, ripples from its birth, should have a distinct signature unlike those predicted by inflation. Future telescopes designed to probe these waves could, in theory, spot the difference, offering the first hard evidence that our universe began not with a solitary bang, but with a cosmic embrace in dimensions beyond our own. So the next time you hear about the Big Bang, consider this. What we call the beginning might just be the latest chapter in an epic far grander than we imagined. A story written not in 3 dimensions, but in the unseen geometry of the bulk, where universes are born, die, and rise again in an eternal dance of creation. Imagine holding a cube in your hands, a simple 6-sided shape with edges you can trace with your fingers. Now try picturing its 4-dimensional cousin, the hypercube. Your brain rebels because evolution wired us to navigate a 3-dimensional world, yet mathematics insists this higher dimensional object exists. Here's the wild part. Even if we can't see or touch a hypercube directly, its presence might leave traces in our universe like a ghost casting shadows on a wall. These aren't literal shadows of light and dark, but mathematical projections, slices of higher dimensional reality bleeding into our perceptual limits. Take that hypercube. When it passes through our 3-dimensional plane, we wouldn't see the whole structure, just the parts intersecting with our space. The result, a shape that morphs in impossible ways, like a cube that grows smaller cubes from its faces or a polyhedron that defies Euclidean rules. These shadows aren't arbitrary. They follow precise geometric laws, revealing glimpses of the hypercube's true form the way a flatlander might infer a sphere from the changing diameter of a circle passing through their two-dimensional world. Artists and mathematicians have visualized this for years, creating animations where hypercubes rotate in 4D space, their 3D cross-sections twisting and reconfiguring in ways that feel alien yet eerily symmetrical. But hypercubes aren't the only higher-dimensional objects that might cast shadows. String theory suggests that all particles could be vibrations of tiny, higher-dimensional strings, their properties determined by how they're sliced by our 3D perspective. An electron's charge or a quark's mass might just be the three-dimensional echo of intricate geometries vibrating in 6 or 7 compactified dimensions. It's like listening to a symphony through a single keyhole. You catch fragments of the music, but the full orchestration remains hidden. Some physicists speculate that dark matter could be another kind of shadow particles bound to a nearby brane whose gravitational influence leaks into our universe like a hand pressing against a curtain. Others wonder if quantum entanglement's spooky connections are threads stretching through higher dimensions, tying particles together in ways that only look instantaneous from our limited vantage point. Even the cosmic microwave background's faint irregularities might encode hints of higher dimensional topology, like wrinkles in a sheet revealing the shape of the mattress beneath. The most tantalizing idea, these shadows might not just be theoretical curiosities. If higher dimensions exist, their influence could warp the behavior of particles in detectable ways. Experiments searching for tiny deviations in gravity's strength at microscopic scales or anomalies in particle collisions are, in essence, hunting for these dimensional echoes. Every unexplained result, every flicker in a detector that defies the standard model, could be a higher dimensional fingerprint waiting to be decoded. So next time you see a shadow stretching long at sunset, consider this. The universe might be full of far stranger silhouettes, shapes not cast by light, but by dimensions just beyond the edges of perception. Reality, it seems, is always holding something back. What if the speed of light isn't a universal constant at all, just a local speed limit in our three-dimensional corner of reality? This is the startling possibility lurking in some higher dimensional theories, that the laws of physics we take as gospel might be mere bylaws specific to the dimensional neighborhood we call home. Picture a library where every floor has its own rules. On one level, silence is enforced while another allows lively discussion. Now replace floors with dimensions, and you've got the essence of dimension-dependent laws. The universe might not play by one rulebook, but by layers of them, each tailored to the geometry of its dimensional realm. Take light's cosmic speed limit, 300,000 kilometers per second in a vacuum. That number seems etched into the fabric of our universe, governing everything from starlight's journey to the workings of your smartphone's GPS. But what if it's only fixed here in our familiar three spatial dimensions? In higher dimensional spaces, photons might race faster or slower depending on how those extra dimensions curve or compactify. Imagine a highway where cars suddenly accelerate when they merge onto an overpass you can't see. That's the kind of variability some models propose for light in a multidimensional cosmos. Gravity could be even more dramatically affected. String theory suggests that what we perceive as gravity's weakness might stem from its freedom to spread into extra dimensions, diluting its strength like ink dispersing in water. But if those hidden dimensions aren't uniformly tiny, if some are larger or warped in specific ways, gravity's pull could vary wildly based on where and how it's measured. It's as if we've been using a single map to navigate a city that secretly has neighborhoods where compasses spin randomly and distances stretch unpredictably. Even time itself might bend to dimensional rules. If higher dimensions allow closed time-like curves, loops where cause and effect tangle, then the arrow of time we experience could be a flatter, simpler version of a far richer temporal landscape. Atomic clocks here tick steadily forward, but in a 5- or 6-dimensional pocket of reality, particles might oscillate between past and future states like pendulums swinging in directions we can't point to. The implications would rewrite not just physics but philosophy. Constants like Planck's length or the fine structure ratio cornerstones of quantum mechanics could turn out to be regional ordinances rather than cosmic decrees. The universe might be a patchwork of dimensional domains, each with its own physics, occasionally brushing against ours in ways that leave anomalies in particle colliders or unexplained gaps in astrophysical data. Experiments are already hunting for these cracks in reality's facade. By probing gravity at microscopic scales or searching for variations in light's behavior under extreme conditions, scientists hope to catch whispers of dimensions where the rules shift. Until then, every unexplained measurement, every deviation from prediction hangs in the air like a question. Are we seeing noise or the first hints that reality's rulebook has pages we've yet to read? Cosmic strings sound like something ripped from a physicist's wildest sci-fi draft. Hypothetical cracks in spacetime so dense, a single inch could weigh more than Mount Everest. But these bizarre structures might not just be theoretical oddities. They could be fossilized evidence of hidden dimensions, wrinkles left behind when the universe's fabric first snapped into place. Picture the early cosmos as a rapidly cooling vat of molten glass. As it solidifies, imperfections form tiny ripples and fractures locked into the structure. Now imagine that process playing out not in 3 dimensions, but in 10 or 11, with extra dimensions crumpling and folding as spacetime took shape. Cosmic strings could be the scars of that violent cosmic origami, one-dimensional defects where the collapsing geometry of higher dimensions got tangled like a snagged thread in a sweater. Unlike black holes or stars, cosmic strings wouldn't have ends. They'd either form infinite loops or stretch across the entire universe, their gravitational fields warping light and time around them like invisible fishing lines in a cosmic pond. If one passed through Earth, we might not feel it directly, but its wake could distort the apparent positions of distant galaxies or create double images of the same quasar in the night sky. The real giveaway, though, would be the string's gravitational fingerprints, sharp, step-like disruptions in spacetime called Kaiser-Stebbins effects, where light from behind the string gets abruptly blue shifted on one side and red shifted on the other. It's as if the universe itself had a seam we never noticed, and the light passing through reveals the puckered stitching. But here's where hidden dimensions enter the story. Some string theory models suggest these cosmic defects aren't just wrinkles in familiar spacetime, they're relics of higher dimensional processes, like echoes of a shout in a room we can't enter. When the extra dimensions predicted by string theory compactified, curling up into their current microscopic forms, their collapse might have left behind these one-dimensional knots, much like ice cracking as it freezes. The string's properties, their tension, their stability, could encode secrets about the geometry of those vanished higher dimensions, offering clues to questions we've barely learned to ask. The hunt for cosmic strings is already underway. Astronomers scour galaxy surveys for telltale lensing patterns, while pulsar timing arrays listen for the gravitational waves static these strings might emit as they vibrate or snap. Even the cosmic microwave background, the afterglow of the Big Bang, could bear their imprint, tiny temperature fluctuations shaped by strings stretching across the infant universe. So far, no definitive detection has been made, but absence of proof isn't proof of absence. Like fishing in an ocean where the lines are invisible, we might just need better nets. If cosmic strings exist, they'd be more than cosmic curiosities. They'd be living fossils from the birth of spacetime itself. Each one could be a cipher, a message in code about the universe's true dimensionality, waiting for us to crack it. And that's the thrill of the chase. Even the emptiest patch of sky might be threaded with clues, if only we learn how to look. gravitational waves have already revolutionized astronomy. Ripples in space-time first detected in 2015, when black holes collided a billion light-years away. But what if the waves we've observed so far are just the opening act? Hidden dimensions might be orchestrating an entire symphony of vibrations, frequencies so subtle they've slipped past our detectors until now. Picture a tuning fork struck in an empty room. You hear the clear, pure tone, but beneath it, the air hums with harmonics, higher, fainter notes that reveal the room's hidden acoustics. Similarly, the universe's gravitational wave background could carry dimensional echoes, vibrations from extra dimensions ringing like ghostly overtones in the fabric of space-time. This idea hinges on how dimensions might vibrate. Just as a guitar string can produce different notes depending on how it's plucked, compactified dimensions could oscillate in specific patterns dictated by their shape and size. Some models suggest these vibrations would generate unique gravitational wave signatures, frequencies too high or too low for current observatories like LIGO to catch, but within reach of next-generation detectors like the Laser Interferometer Space Antenna, or LISA. Imagine floating 3 spacecraft millions of miles apart, using lasers to measure distortions smaller than an atom. That's LISA Plan, a space-based ear fine-tuned to hear the universe's faintest whispers, including potential dimensional harmonics. The math behind this is mesmerizing. If extra dimensions exist, their oscillations would warp space-time in ways that imprint telltale patterns on passing gravitational waves. Some frequencies might cluster around specific values, like notes on a scale, reflecting the geometry of those hidden dimensions. Others could appear as interference patterns, ripples that cancel or amplify in ways that betray their multidimensional origins. It's as if the cosmos were a drumhead, and every vibration carries clues about its hidden curvature. But why would these vibrations manifest gravitationally? In theories like string theory, gravity isn't just another force, it's the curvature of spacetime itself, sensitive to every dimensional quiver. When compactified dimensions wobble, they don't just jiggle particles or light, they distort the very stage reality plays on. That's why gravitational waves are the perfect messenger. They're not confined to our brain like electromagnetic waves, but free to carry news from the bulk, the higher dimensional space beyond our perception. The implications are staggering. If future observatories detect these dimensional resonances, it wouldn't just confirm hidden dimensions, it could reveal their shapes. Different geometries, whether Calabi-Yau manifolds or warped throats, would vibrate at distinct frequencies, like musical instruments made of spacetime. By analyzing these gravitational fingerprints, scientists might reverse engineer the universe's hidden architecture, decoding the geometry woven into dimensions we can't see. And the hunt isn't limited to high frequencies. Some models predict ultra-low frequency waves from cosmic strings or brane collisions, oscillations so slow they take years to complete. Pulsar timing arrays, networks of dead stars acting as galactic metronomes, are already listening for these deep cosmic drones. A single deviation in a pulsar's rhythm could signal a dimensional tremor, a distant drumbeat from the bulk. Of course, skeptics argue these signals might blend into the noise of merging black holes or neutron stars. But that's the beauty of the quest. Every unexplained ripple in the data is a window, however foggy, into dimensions beyond our own. The universe has never been shy about hiding its secrets in plain sight. We just need to learn how to listen. Consciousness might be the most baffling frontier in science, a phenomenon so intimate we experience it every moment, yet so elusive it defies even the sharpest definitions. But what if the mystery isn't just in our brains, but in the very fabric of space-time? Some theorists propose a radical idea. Consciousness could be a higher dimensional process, leaking into our three-dimensional world like sunlight through a prism. Think of your mind not as a product of neurons alone, but as a multidimensional symphony with harmonies resonating in directions we can't point to. this isn't just philosophical musing. The brain's neural networks form staggeringly complex geometries patterns that mathematically resemble fractals or even projections of higher dimensional structures. When neurons fire, they don't just communicate in straight lines, they create dynamic webs of activity that hint at deeper, unseen layers of organization. It's like watching shadows on a cave wall and realizing they're cast by objects moving in a world you can't access. Could consciousness be the shadow of something far richer, playing out in dimensions beyond our perceptual reach? The idea gains traction when you consider quirks of human experience. Near-death accounts, for instance, often describe sensations of floating outside the body or perceiving events from impossible angles, almost as if consciousness briefly untethers from three-dimensional constraints. Even mundane déjà vu might be a glitch in our dimensional interface, a fleeting overlap with parallel timelines or higher dimensional folds. And then there's the hard problem of consciousness itself, why subjective experience exists at all. If the universe is fundamentally mathematical, as physics suggests, why does it feel like something to be alive? Higher dimensions might offer a loophole, a realm where information processing transcends computation and becomes experience. Skeptics, of course, dismiss this as speculative, but consider this. Physics already treats particles as multidimensional entities in string theory. If electrons can vibrate in hidden dimensions, why not the patterns of thought? Some models even suggest that quantum processes in the brain, like those in microtubules, could interact with higher dimensional fields, weaving consciousness from threads of reality we've yet to map. It's a controversial notion, but no more so than the multiverse or dark matter once were. The implications are staggering. If consciousness taps into extra dimensions, it wouldn't just reshape neuroscience, it would redefine reality. Suddenly, phenomena like telepathy or precognition might not break the laws of physics but operate through hidden geometries. Meditation or psychedelics, which alter perception so profoundly, might temporarily loosen our dimensional anchors, letting us glimpse the wider tapestry. Even artificial intelligence, if it ever achieves true awareness, might require architectures that mirror these deeper structures. Of course, proving any of this is another challenge. But the universe has never been shy about hiding its truths in plain sight. Every time you ponder a thought or feel an emotion, you might be brushing against dimensions science is only beginning to imagine. Consciousness could be the ultimate clue, not just to who we are, but to what the universe really is. Astronomers have catalogued the heavens for centuries, mapping stars so thoroughly that their births, lives, and deaths follow predictable scripts until they don't. In recent decades, telescopes have captured something unsettling: stars vanishing without a trace, not dimming, not exploding, but disappearing mid-observation as if snipped from the cosmos. One moment they're there, burning steadily, the next they're gone, leaving behind empty patches of sky where physics says there should be supernova remnants or fading embers. The most famous case, in 1952, a star in the constellation Lupus blazed at magnitude 14.5, then vanished from photographic plates without explanation. No debris, no light echoes, just silence. Could these stellar ghosts be slipping into dimensions beyond our own? The math behind this is stranger than fiction. If higher dimensions exist, they might not just hide passively, they could actively swallow matter under rare conditions. Picture a star nearing the end of its life, its core collapsing under gravity's crush. Normally, this leads to a supernova or black hole. But in models with extra dimensions, the collapse might trigger a phase transition, a cosmic version of water freezing into ice where space-time itself reconfigures around the star, funneling it into a higher dimensional state. It's like a ship falling off the edge of a flat Earth, except instead of plunging into an abyss, the star steps sideways into a direction we can't perceive. From our three-dimensional vantage point, it would simply wink out, leaving no detectable energy behind. No explosion, no warning, just absence. these disappearances challenge everything we know about stellar life cycles. Traditional astrophysics has no room for stars to dematerialize. Energy can't just dissolve. But if matter is crossing dimensional boundaries, the rules change. Some theories suggest that compactified dimensions, those tiny, curled-up realms string theory proposes, could momentarily unfurl near extreme gravitational fields, creating temporary bridges between dimensional layers. A dying star's collapse might be the match that lights this bridge, its mass flaring into higher dimensions like steam escaping a kettle. What's left behind? Not even a black hole, just a cold, star-shaped blank in the cosmos. The hunt for answers is turning astronomers into cosmic detectives. Projects like the Vanishing and Appearing Sources during a century of observations, VASCO survey scour historical data for more cases, while modern telescopes monitor millions of stars nightly, searching for real-time disappearances. The key clue: if dimensional shifts are to blame, vanishing stars should leave subtle gravitational ripples, not the violent waves of colliding black holes, but faint tremors in spacetime's fabric, like the after ring of a bell struck in another room. Next-generation gravitational wave detectors might catch these whispers, especially if multiple stars vanish in similar regions, hinting at dimensional fault lines in the universe. Skeptics argue these stars could be failing black holes, objects so dense they absorb light without the usual accretion disk fireworks. Others propose exotic physics like quark nova, where stars condense into ultra-dense quark matter without exploding. But the dimensional hypothesis lingers because it solves a deeper puzzle: where the energy goes. If a star's mass isn't being converted into radiation or compressed into a singularity, higher dimensions offer a radical but mathematically coherent exit. The implications are staggering. If stars can step off our dimensional stage, what else might be slipping through unseen? Planets, even civilizations. The universe has always been a master of concealment, hiding 95% of its composition in dark matter and energy. Now it might be harboring entire stellar graveyards in dimensions we're only beginning to theorize. Every time a star vanishes without cause, it's not just a mystery, it's a dare. The cosmos is daring us to look deeper, to question not just what we see, but where we're looking from. Picture living in a world where everything exists on a single flat plane, a universe with no up or down, just length and width. In this two-dimensional reality, you'd be a geometric shape, a circle, a triangle, maybe a jagged polygon moving along a surface where the concept of depth is as unimaginable as a color beyond the rainbow. This is the essence of the 2D universe thought experiment, a brilliant way to grasp how higher dimensional beings might interact with our three-dimensional world in ways we can't perceive. Let's bring this to life. Imagine you're a square living in Flatland, the fictional 2D world dreamed up by mathematician Edwin Abbott in 1884. To you, everything appears as lines, your friends are line segments, your house is a collection of angles, and if another shape approaches, you only see the part of them currently crossing your one-dimensional line of sight. Now suppose a three-dimensional sphere descends into Flatland. From your perspective as the square, the sphere would first appear as a single point, the moment its surface touches your plane. As it passes through, that point would grow into a circle, expanding to its maximum diameter before shrinking back to a point and vanishing. You'd have no frame of reference to understand what just happened. To you, it's a circle that mysteriously materialized, changed size, and disappeared. The sphere, existing in 3D, could observe all of Flatland at once, seeing inside closed shapes behind obstacles, even the inner workings of your 2D body, without you ever realizing it was there. This isn't just a whimsical scenario, it's a direct analogy for how beings from higher dimensions might interact with our 3D universe. Just as the sphere could move above Flatland in a direction the square can't comprehend, a 4D being could step outside our spatial reality, observing and manipulating our world in ways that seem impossible. They could reach inside sealed containers, see the interiors of our organs without cutting us open, or even rearrange matter in ways that appear as miracles or terrifying violations of physics. It's like a hand dipping into a pond. To the fish, the fingers appear and disappear unpredictably, bending the water's surface in directions their 2D perception can't reconcile. Now take this further. In Flatland, the square would never grasp the sphere's true nature without higher dimensional intuition. Similarly, our brains hardwired for 3D might be incapable of perceiving 4D phenomena directly. Any interaction with higher dimensions could manifest as inexplicable anomalies, objects appearing or vanishing, forces acting without cause, or visions that defy logic. Some theorists even suggest this could explain certain paranormal experiences, UFO sightings, ghostly apparitions, or spontaneous healings, as fleeting brushes with entities or energies operating in dimensions beyond our own. But the real power of this thought experiment isn't just in imagining higher dimensions. It's in revealing how limited our perception might be. Just as the square can't conceive of volume, we might be blind to the full texture of reality. The particles we think are fundamental could be vibrations in higher dimensional strings. The forces we measure might be shadows of interactions occurring in directions we can't point to. Even time, which feels linear to us, could be just one slice of a richer, multidimensional timeline. So the next time you pick up a book or scroll on your phone, consider this. The flat surface you're touching might be more than it seems. Reality could be teeming with depth. We've yet to fathom dimensions where the ordinary becomes extraordinary, and the impossible is just a matter of perspective. Black holes are often painted as cosmic monsters, voracious pits where gravity wins forever, crushing everything into oblivion. But what if their infamous singularities aren't in points at all? What if they're gateways, twisting the fabric of reality so violently that matter isn't destroyed, just rerouted into dimensions we can't see? This wild idea isn't pulled from science fiction. It emerges straight from the math of general relativity and string theory, where the infinite density of a singularity might not be a dead end but a bridge. Picture a black hole's singularity as a cosmic drain. In classic physics, it's where space-time curvature becomes infinite and all known laws break down. But some interpretations suggest this breakdown isn't annihilation, it's a transformation. Just as water spiraling down a drain doesn't vanish but flows somewhere else, matter crushed by a singularity might be ejected into higher dimensional space or even another universe. The equations hint that singularities could tunnel through space-time like wrinkles in a folded sheet, connecting distant points, or dimensions via shortcuts called quantum wormholes. String theory turbocharges this idea. If extra dimensions exist, a singularity might not just crush matter into nothingness, it could unravel particles into their fundamental strings, then reweave them in a higher dimensional realm. Imagine throwing a ball of yarn into a fan. The threads tangle chaotically at first, but if the fan blades are tuned just right, they might knit the yarn into a new pattern. Similarly, a black hole's extreme physics might recycle matter through hidden dimensions, repackaging it into forms our 3D universe can't comprehend. The real smoking gun, Hawking radiation. Black holes slowly evaporate, emitting particles over eons. Some theorists argue this energy bleed could carry traces of higher dimensional information, like echoes from the other side of the dimensional divide. It's as if the black hole isn't just decaying, but broadcasting faint signals from where its captured matter truly went. Of course, skeptics counter that singularities are mathematical anomalies, not destinations. But if even a fraction of the math holds, black holes might be less like tombs and more like revolving doors swinging matter into realms beyond our imagination. The next time you see an artist's rendering of a black hole's inky abyss, look closer. That darkness might not be the end. It could be the universe's most extreme passport stamp. At the smallest scales, imaginable trillions of times tinier than an atom spacetime doesn't behave like the smooth, predictable fabric we're used to. Instead, it churns with violent turbulence, a frothing sea of chaos physicists call quantum foam. Imagine zooming in on the surface of a calm lake until individual water molecules become visible. What seemed flat and serene now boils with frantic motion, molecules colliding, waves forming and dissolving in an instant. Now replace the water with spacetime itself, and you've got a glimpse of the universe's raw, turbulent underbelly. This isn't just microscopic roughness. Quantum foam represents spacetime's fundamental instability at the Planck scale, distances so small, around 10 to the negative 35 meters, that the very concepts of here and now break down. In this frenzied realm, wormholes flicker in and out of existence like bubbles in a soda, while particles and antiparticles emerge from nothingness before annihilating each other. But here's the twist: these aren't just random fluctuations. Some theories suggest quantum foam's chaos might be the fingerprint of higher dimensions crumpling and unfolding at speeds beyond perception. It's as if spacetime isn't just vibrating, it's shuddering in directions we can't see. The math behind this is staggering. Just as foam on a cappuccino consists of countless tiny bubbles, quantum foam's structure could be woven from tiny, compactified dimensions twisted into intricate shapes like Calabi-Yau manifolds that continuously warp and reconfigure. One moment, 6 extra dimensions might be tightly curled. The next, they've unfurled just enough to allow a particle to briefly step outside our familiar 3. These aren't gentle changes either. The energy involved is so immense that if a single Planck-scale wormhole lasted a fraction longer, it could theoretically unleash enough power to vaporize a planet. Thankfully, the universe's self-correcting mechanisms keep these explosions fleeting. Quantum foam's existence isn't just theoretical. Its effects might subtly alter how light travels across the cosmos. When gamma rays journey billions of light years to reach Earth, the shortest wavelength photons should arrive slightly delayed if spacetime's foamy texture disrupts their path, like a bee navigating a storm instead of flying through open air. Incredibly, observations from telescopes like Fermi-LT have detected hints of these delays, as if the universe itself is pixelated at the smallest scales. But the most mind-bending possibility, quantum foam's chaos might not be random at all. Some models propose that what we perceive as turbulence could actually be the shadows of higher dimensional physics, like watching a 2D being try to interpret the ripples from a stone thrown into a pond they can't perceive. If true, then every flickering wormhole, every virtual particle pair, is a message from dimensions we've yet to map, written in the language of spacetime's fury. The foam isn't just the universe's smallest scale. It might be its most revealing. Supersymmetry was supposed to be physics' grand unification, a theory so elegant it would neatly tie together all fundamental forces by positing that every known particle has a hidden, heavier twin. But decades of particle collider searches have turned up empty-handed, leaving scientists wondering, did we misunderstand supersymmetry's rules, or are we missing a crucial piece of the puzzle? Hidden dimensions might hold the answer, transforming supersymmetry from a near miss into a multidimensional symphony. At its core, supersymmetry, or SUSY for short, aims to balance the cosmic ledger. In our current standard model, particles fall into 2 categories: fermions like electrons and quarks that make up matter, and bosons like photons and gluons that carry forces. SUSY proposes that every fermion has a bosonic partner and vice versa. An electron's counterpart would be the selectron, a photon's would be the photino. These particles could explain dark matter, stabilize the Higgs boson's mass, and unify gravity with quantum forces, if only they'd show up in experiments. Here's where dimensions come in. What if sparticles aren't just heavier versions of familiar particles, but vibrations echoing through extra-dimensional space? Picture a guitar string playing multiple notes simultaneously. The fundamental tone represents our known particles, while the harmonics, fainter and higher pitched, could be their supersymmetric partners. In string theory, where particles are tiny vibrating strings, extra dimensions provide the stage for these harmonics, with their compactified shapes determining the particle's properties. An electron-selectron twin might not be a distinct object, but the same string vibrating in a higher dimensional mode, like a melody played on a flute versus a violin. The math reveals something profound. If extra dimensions exist, they could resolve Sussy's biggest headache: why particles are so much heavier than their standard model counterparts. Normally, Sussy predicts partners should be within detectability range of colliders like the LHC. But if particles are tied to higher dimensional vibrations, their mass might scale with the size and curvature of those hidden dimensions. Imagine trying to hear a bell ringing in a sealed basement while you stand on the roof. The sound would be muffled, its energy dissipated. Similarly, particles might be heavy because their true vibrations leak into dimensions we can't probe directly. This reshapes how we hunt for supersymmetry. Instead of searching for particles in collision debris, experiments might look for subtle anomalies, excess energy bleeding into higher dimensions during particle collisions, or unexpected patterns in cosmic rays. Some models even suggest that dark matter, long thought to be the lightest supersymmetric particle, could be a higher dimensional vibration trapped in our universe's geometry, its ghostly presence a direct result of dimensional harmonics. Critics argue this stretches Sussy beyond falsifiability, but the theory's elegance is hard to dismiss. Hidden dimensions wouldn't just rescue supersymmetry, they'd elevate it, transforming particles from missing puzzle pieces into notes in a multidimensional composition. Every empty search at the LHC might not be a failure, but a clue. The music of the universe isn't playing in 3 dimensions alone. The symphony is richer, and the conductor's baton is waving in directions we're only beginning to imagine. Imagine floating alone in the void of deep space, no stars, no planets, just infinite blackness, when suddenly consciousness flickers to life. You remember a past, a world, a history, but none of it ever existed. You're a Boltzmann brain, a self-aware entity spontaneously assembled by random quantum fluctuations, destined to dissolve back into chaos moments after forming. This bizarre thought experiment, dreamed up by physicist Ludwig Boltzmann in the 19th century, suggests something unsettling. Given enough time, even the most improbable events become certainties, including the emergence of entire conscious minds from pure randomness. But what if this paradox isn't just a quirk of statistics? What if higher dimensions make these phantom minds far more likely and far stranger than we ever imagined? The classic Boltzmann brain scenario plays out in an endless, chaotic universe. Given infinite time, particles bouncing randomly will eventually arrange themselves into any possible configuration, no matter how unlikely, including a fully formed brain complete with false memories. The odds astronomical, but in a cosmos stretched across eternity, even the impossible becomes inevitable. Now, fold extra dimensions into the equation. If our universe is a 3-dimensional membrane floating in a higher dimensional bulk, the rules change dramatically. Quantum fluctuations wouldn't just rearrange particles in our familiar space, they'd ripple through unseen dimensions, creating structures impossible in a 3D world. A Boltzmann brain here might not be a lone, disembodied organ, but a higher dimensional entity, its consciousness woven through compactified directions we can't perceive. Think of it like this: in our 3-dimensional world, assembling a functioning brain by chance is like rolling a million dice and getting all 6s. But if those dice could also land on hidden faces sides representing 4th, 5th, or 11th dimensional states, the probability of winning skyrockets. Suddenly, Boltzmann brains aren't just rare flukes, they're inevitable byproducts of a multidimensional reality. Some string theory models even suggest that these minds wouldn't just emerge randomly, they'd be drawn like moths to the structural valleys of Calabi-Yau shapes where extra dimensions naturally stabilize complex vibrations. A Boltzmann brain in higher dimensions might not dissolve instantly, but persist, its thoughts echoing through folds of space-time like whispers in a cathedral. But here's where it gets truly unsettling. If consciousness can arise from pure chaos in hidden dimensions, how do we know we're not Boltzmann brains ourselves? Our sense of continuity, our memories, even the laws of physics we take as gospel, could all be illusions woven by random fluctuations in a realm we can't access. The universe's apparent age and order might just be a convincing backdrop generated by a mind that formed 5 seconds ago. It's not just solipsism, it's solipsism with extra dimensions where the self, questioning its existence, might be a transient knot in the geometry of a higher dimensional foam. Yet there's a twist. Some physicists argue that higher dimensions might actually protect us from the Boltzmann nightmare. If compactified dimensions impose constraints on quantum fluctuations, like a sieve filtering out unstable configurations, then spontaneous consciousness becomes less probable, not more. The same structures that allow strings to vibrate into particles could prevent randomness from assembling coherent minds. It's the cosmic equivalent of a casino where the dice are subtly weighted against rolling a perfect hand. The irony is delicious. What began as a paradox about entropy and probability now hinges on the shape of reality's hidden architecture. Boltzmann brains force us to confront not just the fragility of our existence, but the very nature of what existence means in a multidimensional cosmos. Are we enduring beings in a lawful universe or fleeting sparks in a higher dimensional chaos? The answer might lie in directions we can't point to, where the line between mind and void blurs into the geometry of the unseen. What if the key to unlocking faster than light travel isn't some sleek warp drive or exotic fuel, but a hidden shortcut through dimensions we can't see? The idea of advanced civilizations mastering extra dimensions isn't just sci-fi, it's a frontier some physicists take seriously. Picture an alien species millions of years ahead of us, not just technologically but dimensionally. While we strain against the speed of light's limit, they might navigate higher dimensional space like sailors using trade winds, bending the rules of reality in ways we can barely comprehend. Consider how we perceive dimensions. To a 2D creature, a 3D being could appear to teleport by stepping out of flatland and back in elsewhere. Now imagine a species that perceives 4, 5, or 11 spatial dimensions. Their ships wouldn't need to outrun light. They could bypass the obstacle entirely by traveling through directions we can't access. The math hints at how certain solutions to Einstein's equations allow for traversable wormholes, but only if exotic matter or higher dimensional geometries stabilize them. It's like building a tunnel through a mountain instead of climbing over it, except the mountain is space-time itself, and the tunnel exists in a direction we can't point to. Communication could be even stranger. If entangled particles share a connection through higher dimensions, as some theories suggest, an advanced civilization might exploit this to send instantaneous messages across light years. We'd perceive it as magic, but to them it could be as routine as radio waves are to us. The Breakthrough Listen project, which scans the cosmos for alien signals, has even considered searching for anomalies that resemble dimensional leakage patterns that can't be explained by conventional physics, like pulses arriving too fast or carrying information that decodes differently in higher dimensional math. But the most haunting possibility, we might not recognize dimensional aliens even if they're right beside us. A 4D being could observe our entire universe at once like an open book, their presence invisible unless they chose to intersect our plane. Ancient myths of gods walking among humans or modern UFO encounters where crafts defy physics. Could these be fleeting interactions with entities operating in dimensions beyond our perception? The truth might not be that we're alone in the universe, but that we're blind to the civilizations sharing our space, separated not by distance but by dimensional geometry. Of course, skeptics argue there's zero evidence, but absence isn't proof. If dimensional travel leaves no traces in our three-dimensional slice, we'd have no way to detect it yet. As our understanding of string theory and quantum gravity deepens, we might inch closer to recognizing signatures of higher dimensional engineering, whether in gravitational wave distortions, particle collider anomalies, or cosmic structures too precise to form naturally. Until then, the possibility lingers. The universe's most advanced species might not be in the stars above us, but in the dimensions around us, hidden in plain sight. Einstein's general relativity paints gravity as the graceful curvature of space-time, a cosmic stage that bends under the weight of stars and planets. Meanwhile, quantum mechanics governs the frenzied dance of particles, where probabilities flicker in and out of existence at the smallest scales. These two theories reign supreme in their respective domains, but when forced to coexist, their equations spiral into nonsense. Infinities erupt, predictions implode, and the fabric of physics tears at the seams. The only way forward, extra dimensions not as speculative garnish, but as mathematical lifelines. Here's why dimensions beyond 4 aren't just convenient, they're unavoidable. Start with string theory's core premise. Particles aren't dots, but tiny vibrating strings. For the math to work, these strings need room to oscillate, not just in the 3 spatial dimensions we know, but in 6 or 7 more, curled into intricate shapes like Calabi-Yau manifolds. Without these extra dimensions, the equations collapse like a house of cards. It's akin to trying to play a symphony with only 3 notes. The music only emerges when the full scale is available. But the urgency runs deeper than string theory. Even in Kaluza-Klein's early attempts to unify gravity and electromagnetism, adding a 5th dimension wasn't optional. It was the only way to make the equations balance. The extra dimension acted like a hidden gear in a cosmic clock, synchronizing forces that otherwise refused to mesh. In modern terms, compactified dimensions provide the pressure valves needed to stabilize quantum gravity. Without them, the energy densities near singularities or in particle collisions become infinite, a mathematical meltdown that extra dimensions neatly resolve by dispersing that energy into hidden directions. Consider gravity's puzzling weakness compared to other forces. In a 3-dimensional world, its inverse square law feels set in stone, but introduce extra dimensions and gravity's strength could leak into higher dimensional space, diluting its effect in our familiar universe. The math reveals this isn't just plausible, it's elegant. Like water seeping through a sponge, gravity's apparent feebleness might simply be a consequence of its multidimensional reach. Quantum entanglement adds another layer of necessity. When particles instantaneously mirror each other across vast distances, they defy locality, the rule that nothing should influence anything else faster than light. But if entangled particles share hidden dimensions like threads passing through the backside of a tapestry, their spooky connection could simply be shortcuts through geometry we can't perceive. The equations only hold if these extra pathways exist. Critics argue that inventing dimensions to fix equations feels ad hoc, but history disagrees. When Dirac's math demanded antimatter in the 1920s, or when Einstein's relativity predicted black holes, these ideas seemed equally fantastical until experiment caught up. The difference now is scale. Testing for dimensions smaller than a proton requires ingenuity, not impossibility. Colliders like the LHC or precision gravity probes at microscopic ranges are the microscopes we're building to peer into this deeper architecture. So while we can't yet reach out and touch a 5th dimension, the numbers leave no choice. The universe isn't just hinting at hidden depths, it's screaming for them. Every unsolved paradox, every fractured theory points toward dimensions we've yet to explore. The math isn't leading us astray, it's lighting the only path forward. Here's a chilling thought: everything you can see, touch, and measure with even our most advanced telescopes makes up a mere 5% of the universe. The rest, a cosmic ghost town of dark matter and dark energy, invisible forces that shape galaxies and accelerate the universe's expansion, yet refuse to interact with light or matter as we know it. For decades, scientists have grappled with this glaring gap in our understanding, probing the shadows for answers. But what if the missing 95% isn't just hiding in plain sight? What if it's spilling into dimensions we can't access, locked away in folds of reality our instruments weren't built to detect? Picture dark matter as an iceberg's submerged bulk. What we observe in galaxies, their unexplained rotations and gravitational lensing, might just be the tip poking above the surface of our three-dimensional perception. The rest could be anchored in higher dimensional space, its full mass and structure extending into directions we can't point to. The math behind this is startlingly elegant. If dark matter particles aren't confined to our brain, the three-dimensional membrane of our universe, but drift freely through the bulk, their gravitational influence would leak into our world like footsteps echoing through a wall, while their true form remains utterly beyond our reach. Dark energy, the even more enigmatic force accelerating the universe's expansion, might be an even stronger candidate for dimensional leakage. One radical theory suggests it's not a mysterious repulsive force at all, but the gravitational pull of a parallel brane drifting near ours in higher dimensional space. Imagine two gigantic sails billowing apart in an unseen wind, their separation stretching the fabric of each individual universe. From our limited vantage point, we wouldn't perceive the higher dimensional mechanics, only the effect, space itself stretching faster and faster, as if pushed by an invisible hand. The implications rewrite our cosmic story. If dark matter and energy are higher dimensional phenomena, then our universe isn't just expanding, it's entangled in a multidimensional dance we've barely begun to fathom. Collisions between branes could trigger cycles of cosmic rebirth, with dark energy's acceleration signaling the approach of the next collision. Even the universe's startlingly smooth distribution of matter, a puzzle known as the horizon problem, might find its explanation in hidden dimensions that once allowed distant regions to interact before compactifying into their current tiny forms. But how do we test such an extraordinary idea? The answer might lie in gravity's faintest whispers. If dark matter bleeds into our dimension from higher realms, its distribution around galaxies could bear subtle fingerprints, unexplained clumps or filaments where gravity's pull deviates from standard models. Experiments like the upcoming LISA Gravitational Wave Observatory or next-generation dark matter detectors could catch these anomalies, revealing not just the nature of the invisible 95%, but the hidden architecture of reality itself. The most humbling possibility, we might be like fish in a pond, unaware that the ripples we feel are caused by forces moving in a world above the water. Dark matter and energy could be the splashes and shadows of a richer cosmos, one that operates on a stage vaster than our senses or our science have yet grasped. Every unexplained galactic rotation, every mysteriously accelerating star, might not be gaps in our knowledge, but signposts pointing toward dimensions waiting to be discovered. So the next time you gaze at the night sky, remember, the darkness between the stars isn't empty. It's a mirror reflecting back the limits of our perception, and perhaps the first clues to a universe far grander than we ever dreamed. We've ventured through realms where gravity leaks into unseen dimensions, where particles whisper across hidden geometries, and where the universe might be a hologram projected from a distant cosmic surface. Each revelation bends our understanding of reality, suggesting that the dimensions we take for granted are just the surface of something infinitely stranger. Imagine a world where dark matter isn't missing, it's simply operating in directions we can't point to, where black holes aren't just cosmic dead ends but bridges to higher dimensional landscapes, where the fabric of spacetime itself churns with quantum foam, hinting at structures so small and complex they redefine emptiness. These aren't just abstract ideas, they're clues that the universe has been hiding its true nature in plain sight. Think about what's at stake. If hidden dimensions exist, they could unify physics' greatest contradictions, merging quantum mechanics and gravity into a single, elegant framework. They might explain why the cosmos is expanding faster than predicted, or why particles behave in ways that defy three-dimensional logic. Even our perception of time could be appended. What feels like an unbreakable arrow might just be one thread in a multidimensional tapestry where past and future coexist in geometries we can't yet map. The implications ripple outward, touching everything from the fate of the universe to the very nature of consciousness. Yet for all we've uncovered, the most exhilarating truth is how much remains uncharted. Every unanswered question, every anomaly in particle colliders, every unexplained galactic rotation is an invitation to dig deeper. Future experiments might soon catch gravity leaking into extra dimensions or capture the echoes of a parallel brane colliding with our own. The next breakthrough could come from a lab, a telescope, or even a re-evaluation of old data that suddenly clicks into place. So stay curious. The universe isn't just stranger than we imagine, it's stranger than we can imagine, with dimensions folded into dimensions, possibilities nested inside possibilities. What we've explored today isn't the end of the journey. It's the first step into a frontier where reality, as we know it, is just the beginning. Keep looking up, keep questioning, and remember, the greatest discoveries often begin with the simplest question: what if there's more?